Hi everyone, I'm Mose Sakashita. Today I'd like to present our work ReMotion, supporting remote collaboration in open space with automatic robotic embodiment. This work was done with Ruidong, Xiaoyi, Hyunju, Michael, Cheng, Malte, and Francois. In design activities, nonverbal cues play an important role. For example, their body position with respect to surrounding objects or collaborators provides implicit information about where they are focusing on in space. Also, head rotations can indicate which part of the design board the collaborator is looking at, or send a signal to initiate face-to-face discussion. Pointing gestures can also be useful to refer to a specific part. Once collaborators are remote, however, it quickly becomes difficult to coordinate these dynamic movements and interactions. We propose a system called ReMotion. ReMotion is a novel system designed to support remote design in open space, and it can facilitate seamless movements through a robotic embodiment, automatically replicating the remote user's body and head movement. Previous work in video conferencing system have been proposed to support collaborative work by rendering facial expressions and gestures on a display, mainly focusing on interactions around a table or a board. Telepresence robots have been used to afford navigation in space and a strong sense of being together, but they require users to control the robot, which can be distracting as they have to divide their attention between the control and the collaborative task. Some other work proposed automatic control for such robots using gesture inputs so that collaborators can focus more on their task. But these systems are also optimized for face-to-face conversations or tasks around a smaller area like a desk or table. In our work, we are considering dynamic interactions that happen in a larger task space, such as Design Studio. We explored how we can properly capture body and head movements and gestures as collaborators walk around in open space, and how we can render them in a way that allows them to understand each other while being able to focus on their design task. In simulating human movements, it is relatively easy to track human movements with a system like Kinect, but reproducing this dynamic movement is more complicated. To simulate the complex and rapid body motion, ReMotion uses an omnidirectional platform that is able to flexibly change its position and orientation at the same time. Here's the side-by-side comparison between our method and the differential drive control that is used for typical telepresence robots. As you can see, the omnidirectional drive effectively replicates the user's movements, but the differential drive occasionally creates movements that are not consistent with the user's movements. This can cause ambiguity about the user's intentions. To render the remote user's attention and facial expressions, our system needs to keep tracking the user's front face and head rotations as they walk around in open space. We first explored a body-mounted camera, but it was too bulky to carry while walking around. We then tested multiple actuated cameras that track the user's position and picked the best shot, but this solution requires a large number of cameras to cover the entire open space. Our final design to capture facial expressions is a neckband system called NeckFace that uses a neural network model to predict facial features and head rotations. These movements are rendered on an articulated display using an avatar created by Avatar SDK. This compact device allows users to freely move in open space. To improve head tracking, we added a 9DOF IMU sensor attached to a pair of glasses and controls the articulated display. Combining these components, ReMotion is able to articulate what the remote user is doing in real time. The robot moves to different positions around the table, synchronizing with the movements of the user. When the user moves to the shelf and looks around different parts of the shelf, the robot also maintains the intents of the user, conveying the user's locus of attention through the combination of body and head movements. Pointing gestures are also critical in making a difference in discussion. To support this, ReMotion includes a pointing arm that indicates the user's general pointing direction using the Kinect tracking. Here are typical interactions during a design review session using ReMotion in a symmetric setting. The robot can convey the notion of switching attention between the artifact and the board. The head rotations can be useful to establish face-to-face conversations or look at specific part for discussion. Collaborators can go back to the board to discuss another aspect of the design. We conducted a preliminary study to evaluate the ReMotion system. The goal of our evaluation was to investigate how our automatic embodiment affects interactions in open space, focusing on body positions in shared space, sense of co-presence, and facilitation of sharing attention. We recruited 13 participants and conducted a within-subject study. We compared the ReMotion system, where they interacted with an automatic robotic embodiment, to the video conferencing tool called OWL, where they had their collaborators' video on the display. To investigate how participants managed their body position in space, we used the heat maps of the recorded body positions. This indicates that in the ReMotion condition, the participants were located mostly within the half of the workspace, reserving the other half of the space for the confederate. While in the old condition, they occupied more space in the room, not taking into account the location of the confederate. This is confirmed with the distribution of distance between the participants and confederate, showing that participants kept their social distance from the remote confederate when they were with the robot. Using a social presence measure, we found that the ReMotion system significantly enhances the sense of co-presence and behavioral interdependence, except for the psychological environment. To understand how the system facilitated sharing of attention, we measured a percentage of the time they shared the same attention during the collaborative task. Our attention measures reveal that in the ReMotion condition, participants shared the same attention as the confederate for longer time. We also counted the number of times when they switched their attention. In our condition, they needed to switch attention for more times because they needed to constantly check the video feed to understand what's happening on the other side. While in the ReMotion condition, they switched their attention less because they were able to see the robot through their peripheral vision to be aware of each other's attention. In summary, we proposed a novel approach of enabling seamless movement in space interactions in open space through the design of ReMotion. ReMotion tracks body, head, and face movements to control a robotic embodiment automatically and reproduce the intentions of a remote collaborator in the shared space. Our preliminary study indicates that ReMotion enhances sense of presence through the robot's movement and facilitates the sharing of attention among collaborators by affording peripheral awareness. Finally, I'd like to thank all the collaborators for this work. I'd also like to thank Avatar SDK for providing free license for research. This work was supported by NSF and Nakajima Foundation. Thank you.